So again, I started off in 69 part B with a picture. We had 2 trains, I think. I'll just draw the kind of locomotive part. Right? I don't know that they have smokestacks anymore, but whatever. So we have the train that's making the sound going this way, right? So the sound's going off in every direction. And then we have our second train, right, going that way. And I know that the train making the sound, so we call that the source, is traveling at a speed of 31.0 meters per second, and I called to the right positive, right? So that got a positive velocity. The speed of the sound itself, so just the V, right, is 343 meters per second, and is the sound that this train's going to hear moving to the right or to the left? All right, so hold on. This train is making noise, right? That's why I drove these like wave fronts, right? So this one's honking its horn, whatever. This train, which is moving this way, hopefully they're kind of on tracks next to each other. This train is moving that way. So the first sound that this train would hear would be this sound in front or this sound in behind? The sound in front, right. And the sound in front is traveling this way, right? So that's to the right, that's positive. So the 343 has to be positive. And then the speed of this train, so this train we call the detector, because the people on that train are going to hear this sound at a shifted frequency and wavelength. So the speed of the detector is 21 meters per second, but since that train's going to the left, we have to give that a negative velocity. All right, I'm not done identifying my variables. I still have the frequency to care about. But follow-up questions about the source of the sound having a positive velocity, the sound itself having a positive velocity, and the detector having a negative velocity. Follow-up issues with that. Yeah, sure.
Does it matter like which side you put as negative and positive?
No, you could have you could have said to the left is negative and to the right is positive, but what would have to still be true is that the source and the sound have the same sign, and the detector has the opposite sign. But yeah, if this one was positive and both of these were negative, equally good. Equally good. Other issues with the signs of the speeds, the velocities. All right, and then the other thing I identified here was that the frequency of the source was 305 hertz, and we want to know what the frequency that we detect is. All right, so I did use the only version of the Doppler effect equation that's on our equation sheet. All right, and then the frequency that the source is emitting is 305, so that goes here. The V without any subscripts is the speed of the sound waves themselves, which is 343. The speed of the detector is negative 21, so I have minus a negative here. And then the source, the speed of the source was positive 31, so I have minus a positive. All right, and then I dealt with my numerator and denominator next. So my numerator ended up being a 364. My denominator ended up being 312. That was actually the same denominator as the previous problem. And then I think I got a little lazy and did those 2 steps at the same time, but I got 356 hertz when I did that. Right? It better be a higher frequency than this, because we know that the waves in front of the train are being bunched together, and since this train is moving into the waves, it's going to hear them even more frequently than a stationary observer would, right? So it's got to be a higher frequency than the 305. It also has to be a higher frequency than we got in part A, where this was stationary. Other issues with 69 part B. All right, great. So I do think that we could use a little reinforcement with that. So I have 2 questions involving the Doppler effect for you guys to work on in your foursomes and threesome, right? The first question is qualitative, and then the second one is using our equation again. And then if we need it, right, we'll do one final example as well if I feel like we need it.